Welcome to homework.
Hello friends, here it is given. An air conditioner with refrigerant 134a. We have to calculate the temperature of refrigerant at the compressor exhaust. That is T2. The rate of heat generated by people in the room. Coefficient of performance of refrigerator. And we have to find minimum volume flow rate. From the table A11 to A13 using fluid properties. At pressure 500 kilopascal and fluid quality to be 1, enthalpy to be 259.36 kilojoule per kg, entropy 0.9242 kilojoule per kg per Kelvin, and specific volume 0.04117 meter cube per kg. At second state, pressure is given 12,000 kilopascal, entropy as at state second to be equal to state 1, enthalpy in second state of adiabatic process 277.45 kilojoule per kg, H3 is equal to 117.79 kilojoule per kg, H4 to be equal to H3, Carnot efficiency is defined as entropy of second state in isentropic process minus H1 divided by H2 minus H1. Carnot efficiency is given 0.75, H2S having the value 277.45 minus H1 259.36 upon H2 minus H1 259.36. So from here enthalpy in second state we will get 283.48 kilojoule per kg. So at pressure P2 is equal to 1200 kilopascal and enthalpy 283.48 kilojoule per kg. Temperature will be 55.5 degrees Celsius. This is the answer of part A. Now answer of B part. Mass flow rate of the refrigerant volume flowing per unit time upon specific volume. This is 100 liter per minute. So it is to be converted into meter cube per second. So 1 meter cube is equal to 1000 liter. 1 minute to be equal to 60 seconds. And specific volume is given 0.04117. So you will get 0.04048 kg per second. Refrigeration load can be calculated. Mass flow rate into change in entropy from state 1 to state 4, that is H1 minus H4, 0.04048 259.36 minus 117.79. So that is 5.731 kilowatt. The rate of heat generated by people in the room. Load of refrigerator minus heat transferred at high temperature minus rate of heat generated by equipment. refrigeration load we have calculated 5.731. Heat transferred at high temperature is 250 upon 60, which is given in the problem. Equipment generating the load 0.9. So on solving it, it is to be 0.665 kilowatt. The power input is defined as mass flow rate into change in enthalpy from state 1 to state 2, that is H2 minus H1. Mass flow rate we have calculated 0.04048. Enthalpy of the fluid in second state is 283.48, and in state 1 it is to be 259.36. So you will get 0.9764 kilowatt, and coefficient of performance is defined as load of refrigerator and upon power input. So 5.731 upon 0.9764. So it is to be 5.87. D part. The reversible coefficient of performance of the cycle is defined as temperature of low junction or refrigerant space, temperature of high junction minus temperature of low. Substitute the value. Low temperature is 26 degrees Celsius. So 26 plus 273. High temperature is 34. So 34 plus 273 minus 26 plus 273. So on solving it, its coefficient of performance to be 37.38. The corresponding minimum power input we can calculate. Load of refrigerator upon coefficient of performance of reversible cycle. So it is to be 5.731, that already we have calculated. Coefficient of performance in reversible process is 37.38. So it is to be 0.1533 kilowatt. The minimum mass flow rate we can calculate. Power input minimum upon change in enthalpy H2 minus H1, 0.1533 upon 283.48 minus 259.36, that is 0.006358 kg per second. So volume flow rate minimum, mass flow rate minimum into specific volume 0.06358 58 into 0.04117, that is 0.000261 meter cube per second, or in liter you may write 15.7 liter per minute. That you have to convert. So that is the answer of this part. Thanks for watching it.